So we've reviewed the Pythagorean theorem. We've reviewed some trig functions like sine, cosine, and tangent, right? And those are all useful tools in our toolbox if we're looking for a side or an angle of a right triangle, right? It has to be a right triangle. You can test to see if a triangle is a right triangle by doing the Pythagorean theorem and seeing if the sides hold true, right? So if sides A and B are squared and then added together, does that equal the hypotenuse side squared? And if it doesn't, then you know that it's not a right triangle, right? So we only use those tools in our toolbox for right triangles. And we have a couple other tools in our toolbox as well. So there are a couple of special right triangles. And the first one we're going to talk about is a 30, 60, 90 right triangle. And then we have a 45, 45, 90. And we get these numbers by the angles inside the triangle, right? So if we see one angle is 30 and we know it has a right angle by that square, then we can automatically assume that that third angle is going to be 60, right? Because we know that all the angles in a triangle have to add up to 180 degrees. So we know that 30 plus 60 plus 90 equals 180 degrees. And same thing over here, if we know that one side of one angle of a 45, 45, 90 triangle is 45, and we know that there's a square there representing the 90-degree angle, then we know that the third angle has to be 45, because 45 plus 45 plus 90 gives us 180 degrees. Okay, so this is what a 30, 60, 90 triangle looks like. And this is what a 45, 45, 90 triangle looks like. And we're going to talk about how we know that these are the patterns, right, that hold true to these triangles. Like, where did these come from? How were they derived? Why do we just know that if the hypotenuse is h, then the long side of the 30, 60, 90 triangle is root 3 over 2 times h, right? How do we know that the short side is 1/2 h? So we're going to prove why we know that is true below. Okay, so if we have an equilateral triangle meaning that all three sides of the triangle are equal. And so if all three sides of the triangle are equal, then we know that each angle of the triangle is 60 degrees. Okay, so that whole angle is 60 degrees. And if we drop something called a perpendicular bisector, I don't really care if you know that phrase too much. I just want you to know that it's dropping a perpendicular line down the middle of that equilateral triangle. So if we drop a perpendicular bisector down, it cuts this top angle into half, right? So it turns into a 30-degree angle, as you can see. It cuts that side down here that was S. It's an awful S. There we go. That was S into S divided by 2, right? It splits it in half. So now we have 2 S divided by 2's instead of 1 S. And we don't know what this A value is right here, right? That's kind of what we need to look for. So we know right off the bat that our first side that we care about, and I'm just going to erase everything else so we don't get a little confused. So I know right off the bat that the first side is our hypotenuse, and that's an S, right? It's just an arbitrary value, an arbitrary length. We're just going to call it S. And I know because when I dropped that perpendicular bisector down that triangle, right, I end up with an S divided by 2. But what I don't know is this A right here. So using our tools in our toolbox, right, we know the Pythagorean theorem is a squared plus b squared equals c squared, right? We are going to plug in some letters and numbers. So I've done it here for you, but I'm going to do it again because I think it's easier if I walk through it. So if I am plugging in my side lengths, right? My long side is a, so I have a squared, plus my short side, which is s divided by 2 squared, equals s squared, okay? And I know the variables are confusing, but think of it just as a placeholder for maybe a number. So if I have a squared, the first thing I'm going to do is I'm going to subtract s divided by 2 squared from both sides. So I have a squared equals s squared minus s divided by 2 squared. Okay? Right, because whatever I do to one side, I have to do to the other. So if I want to move this s divided by 2 squared over, I have to subtract it from both sides. So now we're going to do out that s divided by 2 squared. We're going to see what we get. So we have a squared equals s squared minus s squared over 4. Because s times s is s squared, and 2 squared is 4. So now we've kind of hit a tricky point, right? We have an s squared, and we're subtracting an s squared over 4 from it. But if you remember, 4 divided by 4 is just equal to 1. And so if this s squared is just 1 s squared, I can just change that to 4 over 4 s squared to give them the same denominator, right? 4 over 4 is the same as 1, so 4 over 4 s squared is the same as 1 s squared. Well, 4 minus 1 is 3. So I end up with a equals 3 s squared over 4. Right, so a squared equals 3s squared over 4. Well, to undo a square, I have to take the square root. So I'm going to take the square root of both sides. So I end up with a equals the square root of 3 times s, because the square root of s squared is just s, the squared and the square root cancel. And I take the square root of 4, which is 2. So I figure out that my a side is root 3 over 2 times s. So if our hypotenuse is s, and our short side, right, is s divided by 2, then our long side is root 3 times s over 2. I'll write that a little better so we can see that a little better. So over 2. And so I care that you know where it comes from, but I am not going to ask you to do this every time. I think it's important that we recognize the pattern, right? So if I were going to plug in numbers as like another example of this pattern, I'll do it in like a dark blue. Like let's say I said that the hypotenuse is 10. Well, if the hypotenuse is 10, then the short side is going to be 5. And then the long side is going to be root 3 times 10 over 2. Well, 10 divided by 2 is just 5. So I end up with 5 root 3. So that would be an example with numbers. Okay. Feel free to rewatch this part again and again. I understand it can be confusing, but essentially we're using variables and numbers and plugging them into the Pythagorean theorem to derive where these special right triangles come from, right? So we can memorize 30, 60, 90, but I think it's important that you know where those side ratios come from. So now that we've done that with 30, 60, 90, we're gonna look at the 45, 45, 90, and it's a little different. So instead of starting with an equilateral triangle, we're actually going to start with a square, right? So if I drop a diagonal down this square, then I end up with a side of S and a side of S and a diagonal of D. And so I know this is a 45, 45, 90 triangle, because every angle in a square is 90 degrees, right? So this is 90, 90, 90, 90. And when we cut a 90-degree angle in half, we get a 45-degree angle, right? So those 90-degree angles turn into 45 for both of them. Okay, and so we're going to do the same thing that we just did. We're going to plug in our variables into the Pythagorean theorem, that a squared plus b squared equals c squared, to figure out where that ratio comes from between the side lengths. But this one's not nearly as like mathematically taxing. So if I plug in, right, this d is my hypotenuse. So I know that I have side length s plus side length s equals the diagonal, or the hypotenuse, squared. Well, s squared plus s squared is just 2s squared, right? We combine like terms. So I get 2s squared equals d squared. And then to undo a square, I have to take the square root. So I end up with root 2. And then to undo a square, right? So s squared, if we take the square root of that, that just ends up as s. So the square root of 2 times s equals the diagonal. So if we look at the side lengths of the triangle, right, we end up with root 2 times the side length, and then these two sides match, because a square cut down the diagonal is really just two isosceles triangles, right? So isosceles meaning that these two side lengths are always going to be the same. So that's where that pattern comes from. And again, if I do an example in like the dark blue, so you can see with numbers what that would mean that if this were 7, then this side would also be 7, and then this side would be 7 times root 2. So feel free to watch this video as many times as you need to kind of understand how we use Pythagorean theorem to come up with the ratios for 30, 60, 90, and 45, 45, 90 triangles. I tried to be as concise and clear as possible, but again, if you need any help, feel free to reach out to me.